Hello, hi everyone. Welcome to JVM Roundabout. So we're live on our YouTube channel. This is our 22nd installment. As you can see, I'm joined by Chris and Roman tonight. So yeah, we're obviously excited for this one. It should be a great one. We're going to be talking about JVM Garbage Collection. So just before we start, obviously, for anyone who's a regular, good to have you again. But for anyone new, welcome. My name is Ben. I work for a company called TRG. So I actually am a recruiter in this space, and alongside that, I run the event to give something back to the community. So we are trying to grow as a community. So you'll be able to see we have a Twitter handle. If you are putting anything online, please just hashtag JVM Roundabout. That really helps us get more followers, more people talking about it. So first up tonight is Chris, senior engineer at a company called DiffBlue, who we're collaborating with tonight. So thanks to everyone from DiffBlue for your efforts tonight and helping to get it organised. And then after that, Roman, principal engineer at Red Hat. He's also a Java champion, so we're obviously delighted to have him speak for us tonight as well. So what I'll do is I will now hand you over to Chris, who's going to start. And if you have any questions, there is a comment section. You can put them in there, and we will, as long as there's not too many, we should get through them. Or if there's loads, we will have to select some, and others we'll have to ask Chris and Roman after on our Slack channel. So I'll hand over to Chris now. Thanks very much.
Cool, thank you. So I'm going to speak a little bit today about some general garbage collection algorithms. So these are effectively building blocks. They're not real production JVM algorithms, but they're the concepts that are used in most of the real collection algorithms. So what am I going to talk about? Basically, so some overviews. I'm going to gloss over a lot of the very tedious detail that's involved in these, apart from a few things which I find are kind of cute little tricks that are played. And I say these are not about specific real-world JVMs. So I'm going to start with a little bit kind of terminology just to make sure we have a sort of shared starting point. So if I talk about an object, I just mean a piece of data in memory. Now, in Java, that's pretty much going to be an object in the Java sense, but it could be any piece of data in memory. I will also talk about pointers and references. They're the same thing. They're just the address of some piece of memory. I'll talk about the heap. The heap is just a section of memory that's used for dynamic allocation. So every time you do a new some class in Java, that's dynamic allocation. It will appear on the heap. I will talk a little bit about stacks as well. So a stack is just a last in, first out structure that stores the sort of per method local state. So things like your local variables, return addresses, things like that. I will also talk about mutators, which is that's effectively the user program. That's the thing that is putting stuff into memory, deleting things from memory, etc., etc. And I'll talk about the allocator, which is the thing that gives you a piece of memory. So when you say new blah, it's the allocator that basically gives you that chunk of memory. I'll also talk a little bit about a couple other concepts. So one is the age of an object. This is a little bit odd in that when we talk about the age of an object, we don't really care about wall clock time. This is about how much work has happened. So when we say an object is of a certain age, that's the amount of allocation that's been performed, memory allocation that's been performed between the time the object was created and the time that object becomes dead. It's a slightly confusing concept, but just think about it as the GC doesn't care about time, it just cares about how much memory pressure there is. And then I'll talk about live objects, which are an object that could possibly be used at some point in the program's lifetime. And I'll talk about dead objects, which are an object that can never be used ever again. I'll occasionally mention working set. By that, I just mean all the live objects in the program at any instant time in time. And I will at times mention the compiler. Now, for Java, what I mean there is the JIT compiler, not the Java C compiler. So I'm going to start with just a kind of key driving concept in garbage collection, that's reachability. Now, garbage collector is not a time machine. It doesn't know what your program is going to be doing in the future. All it knows about is the current state of the program. So what it cares about is reachability. And that is the idea that if there's anywhere in the program you have a reference to an object, then that object is reachable. So it must be considered live because it's always possible that you may use that again in the future. The opposite of that is that if you have no references to an object, then it's absolutely impossible for your program to access that object again, and therefore it's unreachable and it's dead. And it's the unreachable objects that you're trying to find as a garbage collector. Occasionally this gets referred to as liveness as well, so it's another sort of interchangeable term to some degree. So I'm going to start with what is arguably the simplest garbage collecting algorithm, and that's reference counting. I'll rip through this fairly fast because it's probably quite familiar to some people, especially if you've done any kind of iOS programming. Okay. Catching. Right. So if you imagine there's some program here, and we have a stack frame for this method that has the local variables x and y on it. At the first line in the program, or in this method, you allocate some object, and what happens is you get a pointer in this variable x on the stack, points to some object in memory, and we stamp a number on that object, which is how many references to that object there are. And at this point, as it's just been created, there's only one. Then next line, okay, now we have another object that also gets stamped with a reference count. And then in this line, we've added another reference to y into this field F1. So now this object here gets a reference count of 2 because it's now got 2 references into it. And then maybe we change what y points to, points something else. So the reference count for this object here goes back down to 1 because it's lost a reference. And then at some point in the future, in the return statement, you find that the reference here, we've lost the reference to this object, so this reference count goes to 0. Now, when its reference count goes to 0, that means there are no more references left in the program to it, and it can be deleted. So it's quite a kind of simple algorithm. In terms of actually mechanisms how it works, reference counting GCs typically maintain what's called a free list. And a free list is conceptually effectively just a linked list of pieces of memory that are available for allocation. So they're free, they're empty, and they can be used for new objects. And the allocator will basically just take the first thing off of that free list that is large enough to hold the object that you're trying to allocate. And then when you have a dead object, you just link it into the linked list. So it's a fairly sort of fast operation in that sense. Reference counts do need an extra object, an extra field in every object. And that field needs to be large enough to hold the maximum number of references that you could possibly have to an object. So typically that's going to be effectively one whole word, one whole pointer size. And it needs to perform an action every time references are modified. And that's done by what's called a write barrier. And write barrier, again, is a general concept in GC. So I'm going to talk a little bit about write barriers here. Now, like I say, write barrier is effectively just a piece of code that is executed every time a reference is updated. By that, we might mean a reference is added, or it's removed, or it's overwritten. And generally needs quite close cooperation between the garbage collector and the JIT compiler, so that normally you want to kind of inline the write barriers if you can, or inline part of the write barriers for performance reasons. Now, because you're potentially inlining these everywhere a reference is updated, it's quite important to have the write barriers be small and fast, because they're going to end up in a lot of pieces of code that are executed a lot of times. So you'll typically split them into a fast path and a slow path, with the idea that the fast path is effectively a sort of condition gate of, do I need to do any work at this reference update? And a slow path, which is, yes, I do need to do some work, now do the work. And then you'll typically do some like inline the fast path, but don't inline the slow path. So for reference counting, what does the the right barrier look like? So you have a fast path, which looks something like this in pseudocode. So if you imagine this right barrier is triggered for trying to write a reference to an object into this variable var. So the first thing you have to do is check whether the existing value in var is a null or not. If it's not, then you need to remove the reference or decrement the reference count for that thing that it currently points to. And if that thing has now gone to 0, you need to free it. Otherwise, you just overwrite the variable with the new value, and then you update the reference count for that object that you've just created a reference for. That's the fast path. So we hope that should be relatively fast. In the slow path, you actually have to do some serious work, because now you know that this object is dead and you need to collect it. So when you do that, you actually have to first go through all the references that object contains to other objects, and then effectively do the same as the right barrier and go and decrement the reference counts for all those things it points to, potentially having to go and free those as well. And then eventually, once you've done that for all the references in this object, you then can add it to the free list. And that effectively is that object and anything it points to collected. So what are the kind of pros and cons with reference counting? So on the good side, your GC work is actually kind of interleaved with the user program's work. Sometimes that means you can make use of cache locality for performance improvements. You don't have sort of stop the world phases where all your user program work seems to pause for some long period of time. It's also relatively simple and sort of non-invasive, and it can be quite successful. On the downside, you do have to increase your object sizes slightly, and if you've got a lot of objects, that can add up, or if you're in kind of memory constrained situations. The allocation routines can be a bit slow. There's various kind of ways to manage free lists with sort of various performance improvements, but in general, they're not the fastest way of allocating. It has issues with memory fragmentation, which I'll come back to later in the talk. It also has kind of unpredictable performance around assignment operations. So most programmers kind of expect assignment operations to be relatively constant time, modulo whether it's a copy or not. But with reference counting, if you imagine you do an assignment that removes the last reference to a gigantic tree of objects, then that's going to take quite a lot longer time while it goes and collects all those objects that have now become garbage. Also, the reference counts actually need to be atomic as well. So if you've got a multi-threaded system, you've got a whole bunch of atomic operations that have to be done to keep those counts same. But probably the biggest killer is that it doesn't collect cyclic structures. So if you imagine you have a set of objects like this, where you've got some objects around here and a reference into this object here, if you remove that reference, then that object's reference count goes down to 1. And now effectively all these 3 objects are actually garbage because they're not referenced by anything other than themselves, but none of those reference counts ever go back down to 0, so they never get collected. So how do we deal with cycles? One of the ways we deal with them is what's known as tracing collectors. And this is a broad range of different types of garbage collectors, and I'm going to go through some examples here. In fact, all the rest of the examples I'll go through in this talk are tracing collectors. So the idea of tracing collectors is that you effectively just do a tree walk from some routes, which I'll explain in a second, and anything that is reachable from those routes is still alive, and everything else is dead. So in Java, for instance, the roots are effectively your global variables, so static fields, things like that. The stack, because that's where your local variables are stored, and potentially your CPU registers, because your JIT compiler may have done optimizations where references to objects are only in CPU registers for some period of time, and they never make it back onto the stack, for instance. And as I say, the rest of the GC algorithms I'll talk about in this talk are all tracing collectors. So I'm going to start by talking about an algorithm called mark sweep. So if you imagine you have your heap in the middle here, and you have a set of routes which are pointers into the heap, and we've been doing some work and we've filled up our heap, so now we need to do some garbage collecting activity. So the first thing you have to do is stop the world. So stop all the user threads so that while we're doing our GC work, it doesn't change underneath our feet. And then you do a mark phase. And in the mark phase, what you do is you look at each of the routes in turn. In this case, we've got the first route here. We look at this, and you stamp that object with a mark to say it's still alive. And then for each object field, reference field, whatever you want to call it, in that object, you go and mark each of those. So this O1 field, for instance, points to this object, so you mark that. The O2 field, let's say, points to some other object, so you mark that. That object has another object field. Oops, sorry. So that object points back to something that's already been marked, so we don't have to do any more work on that. And let's say this final field here is some kind of primitive type, so we don't have to do work for that field. So at this point, we've reached the sort of bottom of the tree walk from this route, and everything that is reachable has been marked. So you then move to the next route. In this case, we mark that one. It has two primitive fields, so no more work to do there, no references to trace. Go on to the next route, do the same thing. And then when you've hit the end of all your routes, you've marked everything that is reachable from those routes. And that's the end of the mark phase. Then you move on to a sweep phase. So in a sweep phase, you start with effectively a pointer to the first object in the heap. And if it's a marked object, you unmark it. And then you move to the next object. If that's a marked object, again, you unmark it, move to the next object. If the next object is unmarked, then that means it was a dead object. It wasn't reached via tracing, so you can add that to the free list. Then you move to the next object, unmark it, next object, unmark it, next object. This is an unmarked one, so it goes on the free list, next object, unmark it. And once you've hit the end of the heap with your pointer, you can start the world back up again and use this and carry on running. At this point, you've freed the things that were dead. So how does this kind of work in practice? So it uses a free list like reference counting. In this case, you don't actually need a write barrier because we're not tracking pointers as they're modified. That's true for a stop the world mark sweep like this. There are such things as concurrent mark sweep algorithms where they don't stop the world. They do need a write barrier, but I'm not going to cover that in this talk because they're fairly complicated. You also need a little bit of space in objects to mark them when they're doing the mark phase. However, you actually only need a single bit, and you can kind of steal it most of the time. So what do we mean by steal it? So as far as Java, etc. is concerned, an object is just some kind of blob of memory. There's no real structure in that memory. And the JVM also actually adds some of its own kind of invisible headers to objects as well. So there might be things like locks and pointers to type information, maybe thread IDs, things like that. And the fields are effectively just offsets from the base address of the object. So, you know, the type info in this example is at offset 0, the lock is at offset 4, etc. Now, all of the reference fields in here are going to just be pointers, and pointers are actually aligned addresses. And what we mean by that is that they don't point to any possible byte in memory. They typically point to any possible word in memory. And that means that the lower couple of bits of a pointer or reference are always 0. So what you can do is you can steal some of those bits to mark an object. So for instance, given that the JVM internal headers are always at fixed locations, we can use some of those headers. So for instance, in this example, we're going to steal a bit out of the type info. So if you want to mark an object here, what you do is you use the type info and you set the lowest bit of that reference. And then when you want to clear it, you just unset it. And as long as the JVM doesn't need to access that field between you marking it and you clearing it, it's quite happy. So that way, you don't actually need to add any more memory space. You can just steal some bits. So the pros and cons of mark sweep. On the good side, you can collect cyclic structures because you're doing a tree walk and a trace, and you'll always reach everything that's alive. And if it's not reachable, you won't reach it. You pretty much have zero overhead in memory in terms of per object. You don't need a write barrier. The performance is fairly predictable, and you don't need sort of atomic operations. On the downside, allocation can be a bit slow because it's free list based, and you still need a stop the world phase, or you need a stop the world phase rather. So during the time you're doing GC, no other work is going on. You also end up traversing the heap twice at every GC, which can be a bit of a performance problem depending on how your caching works. So you basically have to traverse it once for marking and then again for sweeping. And you can also have a problem with memory fragmentation. So what do we mean by memory fragmentation? So if you imagine a heap like this, let's say the program's been running for some time and we've got a mixture of some objects in the heap which are in blue, and then all the free space that we've collected in grey. After time, you'll find there's a lot of kind of grey holes in amongst your blue. So when you want to allocate an object, this new one here, you suddenly find that actually there are no single contiguous piece of grey memory, free memory here, that you can fit that into. So although you have plenty of free memory in total, you can't actually allocate the object you want to allocate. And the more gaps there are, the more fragmented it's considered to be. So how can we deal with the memory fragmentation issue? So one of the ways we do that is what's known as copying collectors, also known as moving collectors. So I'm just going to run through what's probably the simplest copying collector, which is what's known as semi-space. So semi-space, you notionally split your heap into two halves. You have a from space and you have a to space. And you start off by allocating memory objects in your from space. So you have a pointer that's your allocation pointer. You create objects at the allocation pointer, and then you move the allocation pointer onto the next piece of free space. You keep doing this, doing your allocation, bump the pointer along, allocation, bump the pointer along, and eventually you fill up your heap, or that half of the heap, I should say. And that's the point we need to do at GC. So you move the allocation pointer over to the to space. Again, I should say this is a stop the world collector. So you stop the world, and then you move the allocation pointer over to the to space. And then you also add an additional pointer called the scan pointer, which again points to the beginning of to space. And then, like the other tracing collectors, you start with your roots. And for each root, you look at the object that's pointed to, and you copy it across to the to space at the allocation pointer. And then you bump the allocation pointer. You also write into the old location what's known as a forwarding address. So I'm going to put that in this header here. And that's basically the address of the copy of that object. And then you go to your next route and you do the same again. So you copy it over, leave behind a forwarding address. And the next route, copy it over, leaving behind a forwarding address. Once you've done through all of the routes like that, you then start looking at the scan pointer. The scan pointer here. And you look at this object here, and you follow the references out of that object back into the from space. And all of those things you also need to copy over. So let's take the first case here. So let's say this object field here points to this class, this object over here. It has a forwarding address, which means it's already been copied. So all you do is you overwrite that field with the forwarding address, which means effectively the pointer does that. And again, you look at the next field in that object, and that points to an object that hasn't yet been copied. It's got no forwarding address. So you copy it over, leaving behind a forwarding address, and you update the field. Once you've done all the fields in that object, you bump the scan pointer to the next object. And again, this particular green object here has two primitive fields, so we'll assume there's no work to be done for that. And let's say this one here has got two primitive fields, no work to be done. Let's finally get to this object here that has two object fields. So you look at each of these and say, okay, that one points to an object that's already been copied because it's got a forwarding pointer. So you update that field to point to the copy. Look at the next field, that's also already been copied. So you update the pointer again, and then bump the scan pointer forward. at the point that the scan pointer meets the allocation pointer, that means you trace the entire heap, which means everything in the from space is garbage. So you flip what's from space and to space and start your program off run again, start the world again. And then you do your allocation in the from space here. So nuts and bolts of this. The allocation is great. It's what's known as bump pointer allocation, and that's about the fastest method of doing allocation you can get. It's small code, it's fast, it can be inlined if you want. Freeing objects is basically free. Once you figure out what's dead, you just throw away the entire memory space or effectively overwrite it. You don't need a write barrier. You do need some space in the objects to store a forwarding address. However, you only need that space after you've already copied the object. So typically what you do is you just reuse any existing field in the old version and overwrite it. And then still a mark bit to say this one's been copied. But actually you don't need any more space in the object. In terms of pros and cons, you don't need to maintain a free list. So that gives you a win in terms of allocation speed. You have fast bump pointer allocation. You don't have memory fragmentation anymore. And you only traverse the heap once per GC, because effectively you use your to space where you're copying objects as your work queue. Unfortunately, you do need twice as much memory as the size of the heap, actually kind of twice as much as the size of your working set. And basically you copy everything on every GC, or everything that's live on every GC. So if you have objects that hang around for a long time, they'll get repeatedly copied to and fro between from and to space. So we can deal with the repeated copying a bit with what's known as generational collectors. And this is driven by what's known as the weak generation hypothesis, which is an observation by Dave Unger in 1984, that most objects die young. This actually holds across most types of languages, so imperative, functional, object-oriented. And the idea of generational GCs is that you concentrate your work on the things that are most likely to be dead, so the younger objects. And this, to a large extent, drives most sort of modern GC algorithms, most real-world GC algorithms. So the basic idea of a generational collector is that you, a bit like memory space, you divide your memory into two regions. You have a nursery region and you have an old region. There are different names for these things, but this is the sort of generic name, as it were. And you do your allocation in the nursery, and it's just bump pointer allocation normally. So you do some bunch allocation, you fill up your nursery. At the point that you've filled up your nursery, you do a collection just of the nursery. And you do the normal thing of trace from the roots, copy the things that are live into the old generation, and you throw away anything that's left in the nursery. And then you can do some more allocation, and you need to do another collection once that allocation has filled up the nursery. Now, at this point, as well as the roots that are sort of global, you also have roots that are references in the old generation into the nursery. So the nursery collections, we're only going to collect the nursery, not the old generation. So anything in the old generation that points to anything in the nursery has to be considered. So again, copy over anything that's either referenced from roots or from things in the old generation, copy those over, and then you throw away the nursery again. And then you repeat this of decent collection, decent allocation, and eventually you get to the point where you filled up both your nursery and your old generation, at which point you do a collection of the entire heap from the roots. And this is a full heap collection of everything, including the old generation, so that you end up with just the live objects in the generation. This will be a slower collection because you're collecting more memory. But the idea is that you'll do lots and lots of nursery collections before you ever have to do a full heap collection. So a couple of nuts and bolts again. It's bump pointer allocation, which is fast. Write barriers are needed this time because you need to somehow notice that there are pointers in the old generation into the nursery. So you need to watch for pointers being updated. So the write barriers for generational collector, they're fairly simple. Again, if we have some target object that we want to write a reference to into some memory slot here, then what we need to do is check that the target is in the nursery and that the slot is not in the nursery. And if that's the case, then we need to add this slot into the roots so that we look at this slot when we do a collection. Now, this is a little bit less than ideal because we're actually doing 2 branches in this write barrier, which is not great for performance. So there's some tricks we can play here. If you consider the memory layout of your heap, if you lay out your nursery so it's at one end of the heap, doesn't really matter which end, I'm going to use the lower end of the heap. And if you set your nursery to be a power of 2 size, so in this case 2 to the nursery bits, where nursery bits is 12, and you make sure that's aligned on that boundary, then effectively the lower 12 bits in this case of an address for an object effectively tell you which cover all of the memory addresses in the nursery. So what you can then do in your write barrier is do a bit of bit shifting so that you take the target address and the slot address, you effectively slice off the couple of lower bits. So we effectively shrink it down to something that points to a region rather than an exact address. And then you only have to compare whether the regions are ordered. So if you have if the target region is lower than the slot region, then we have to remember that slot because it's across the boundary into the target. There's a little bit of fuzziness here in that this saves you a branch. You only have to do 1 branch. You do end up adding a few more slots to your roots than you ideally need, but they're fast to deal with at GC time. So it's a trade-off that's worth having because this write barrier we executed a lot. So it's a little trick that gets used quite often. So pros and cons. The long-lived objects are only processed on full heap GCs. Nursery GCs, they're not copied. Once they've been copied once, they'll stay in the old generation until you need to do a full heap. Your nursery will be smaller than your old generation, so your GC pause times are fairly short because you only have to collect the nursery. And you concentrate most of your work on the nursery where they're most likely to be dead objects. On the downside, you need to have a write barrier now, so your pointer updates and things have a little bit of a tax on them. And you need some additional structures to track these old to young roots. So what about real GCs? Well, most GCs don't actually use one of these algorithms. They use some kind of a mix and match sort of hybrid approach. So you get things like a mark compact collector where you do mark sweep, but instead of sweeping, you do a copying type collector to reduce fragmentation. Or you get things like generational mark sweeps where you use copying from the nursery into the old generation, and then in the full heap you do a mark sweep or something like that. Or you get kind of multi-generational collectors, so you have like an Eden space, which is sort of the nursery, and then a survivor space, which is things that survived the nursery collection, and then an old generation, which is things that survived multiple GCs. So there's normally some kind of hybrid approach like that. And that was all I wanted to kind of run through today. Very fast, apologies for that. Do we have any questions? I think we have a few on the comments. Let's see. So, Harish, yeah, you asked, are there any runtimes that use reference counting GCs? How do they officially combat cyclic ref counts? So there are a bunch of versions of reference counting that do kind of graph type operations to try and find cycles. Reference counting GCs work well if you don't generally produce cycles. So for instance, most of Apple's SDKs for both macOS and iOS for a decent amount of time were using reference counting for their API level memory management. So their underlying runtime didn't do GC. It was automated via the APIs. So reference counting quite often is used in cases like that. Let me see. Okay. And then let's see, we have another question here. Desmond.
Yeah, the question, it should show up now. Start showing up. But do you want me to?
Cool. I'm also aware of the time, and I don't want to cut too much into everyone's time.
I think the next question was, what happens when compressed OOPs are enabled, where marks are stored?
Cool. So I don't actually know the answer to that off the top of my head. In the worst case, you, I guess, have to the JVM would effectively add some extra bits onto the structures. That's an implementation detail that, yeah, honestly, I don't know the answer to. In the worst case, you add an extra field around the metadata. The JVM will always have metadata around objects, so yeah.
Cool. I think we'll do another question. Chris will be available for any questions after.
Yep, I will be on Slack.
Yeah, I'll point everyone to our Slack group at the end. So we'll go with one more question, which should come up on the screen, but I'll start reading it from Desmond. It's that you said earlier. Here we go.
Yes, yeah, that's correct. Yes, apologies.
Okay.
Yeah.
Cool. Chris, thanks very much. Really appreciate it. Great talk. Like I just mentioned to all the viewers, I will point you all in the direction of our Slack group at the end, and obviously you can reach out. But Chris, thank you, and we'll get Roman set up for the next presentation. Thanks very much. Okay, Roman at
hello,
Red Hat Java Champion. I'll take it away.
Hello. Thanks, Chris. This was a nice talk. Actually, a great introduction into what I'm going to do. I want to talk about the Shenandoah GC, which is one particular GC in the OpenJDK. And I will take you a little bit deeper than what you've seen so far. So a little overview of what I'm going to talk about. I'll give you a little introduction into the Shenandoah GC, and then I will talk more about the concurrent evacuation and the concurrent routes and why we are doing all this stuff. So introduction. Shenandoah is a garbage collector in the OpenJDK. It is a concurrent GC. So what Chris talked about so far, all the collectors are stop-the-world GCs, which means that whenever the GC kicks in, it needs to stop all the Java threads and then do its work and then resume Java threads. And this can easily take some time. You probably remember from like 10 years ago, so the dreaded GC pauses. But even today with large applications, this can easily take up to several seconds. And the aim here is to solve this GC pause problem, regardless of heap size, regardless of tiny hardware or whatever constrained environment you have. And Shenandoah is also made to be universal in the sense that it has no restrictions on operating systems or hardware-wise or something like this. To put it in context of the other GCs that we have in the OpenJDK, we have the simplest GC is probably the serial GC, which is a copying collector. It has generations, young and old, and it has a copying collection in the young generation and mark compact in the old generation. All of this stuff is stop the world. This is the meaning of the orange boxes here. And it's single-threaded. This is why it's called serial collector. This means that if you have a large heap, this is probably going to take a while. The improvement on this is the parallel collector, which works similar to the serial collector, except that it uses several threads that to do the GC works, which makes it just a little bit faster, or much faster actually. So this is also called the performance GC. If you need high throughput and don't care about latency, then this is probably it. Then we have CMS, the concurrent mark and sweep collector. The name says it all. It's a mark and sweep collector. It's mostly concurrent in the old generation. it doesn't care about concurrency in the young generation because it's usually fast enough. Problem here is that it tends to fragment the heap in the old generation, and at some point, especially if you have long-running application, it's probably fragmenting the heap and causing a full GC, and at this point you are back to having a long GC pause here. G1, this stands for garbage first. It's kind of a hybrid model. It's a compacting GC. It does concurrent marking, but compacting and young generation copying is still done while the world is stopped. The idea here is to manage the amount of work that it does in the compact phase here by picking only those regions of the heap that have lots of garbage and hopefully few live objects, so that this doesn't take too long. It's kind of a managing solution. And then we have those new GCs, Shenandoah GC and ZGC, which are concurrent, all concurrent GCs. They do concurrent marking, concurrent compacting, but so far they are not generational. We are working on generational support for Shenandoah, but it's not there yet. So how does it look like? So we have I want to talk about where these GC pauses come from and how we eliminate them in Shenandoah. So just to break it up a little bit, what's the reason why we need to stop the GC? So we have this marking phase here. This is a stop the world GC, right? So it needs to mark all through the heap. It needs to do the evacuation, which is also called compacting, and it also needs to update all the references, and all this stuff is in the classic GCs done while the world is stopped. There's also the little boxes here, which is the so-called routes. Chris also already mentioned this. So we have the thread stacks, and then we have all sorts of other stuff in the routes here, which is basically internal to the JVM, like JNI handles. We have the code cache, where we have all those constants that the compiler compiled into the code. We have weak references, class loader data, and so on. All these things need to be scanned and take away the pause time. Overall, it's basically O of n performance here, proportional to the live data size here in those big phases, plus the size of the routes. This means if we have many threads or threads with large stacks, this is going to take time away from your pauses. If you use lots of JNI handles, this is going to take time. If you have lots of weak references, then this is going to take away from your pause time. So we need to address all those issues. Shenandoah is solving this in several ways. So first of all, Shenandoah is a regionalized collector, which is similar to what G1 is doing. So the heap is divided into regions. Each region is one of those boxes here. The blue boxes are regions which have objects allocated. The gray ones are empty regions. And as long as the application is running, no GC is done, we don't know what's in them. We have lots of objects in them, but we don't really know. Then we stop the world briefly here for some setup of data structures and scanning the routes. And then we carry on with the application. And while the application is running, we do concurrent marking, which means the GC is marking through the heap here and figuring out which objects are live and which objects are unreachable. The outcome is what you see here. The green, the green ones here are live data. The yellow ones is regions which are selected for collection. So it's basically similar to what G1 does. It picks regions which have little live data and lots of garbage and selects them for further collection later. At this point, we stop the world again, do some shuffling around of data structures and scan the routes for the initial evacuation. And then we copy all those live objects that are remaining in those regions into a new one over here, at which point those objects become unreachable. Then we stop the world again And then we do concurrent updating of references, which means that all the objects that previously pointed to objects in those regions need to be updated to now point to the new copy that we just made here. After we're done with that, we can reclaim all those regions here, the yellow ones. They become free now and are good for further allocation. So this is this, and this region. This is the overview of how one cycle of Shenandoah collection works. Let's start with the concurrent marking. Actually, I don't go into this detail here because this is already done in G1 GC. We do it very similar to what G1 does. If you're interested in that, I suggest you read this book, the Garbage Collection Handbook. If you have any interest in GC or memory management, this is the book to go to. So this is a very the go-to resource for any information if you want to learn about garbage collection. So this is we use the snapshot at the beginning algorithm. This is similar to G1 for concurrent marking. So this is concurrent now. Let's see. I make the concurrent phases green. So let's address the other ones, the evacuation phase and the update references phase. Especially the evacuation, because this is interesting, how to move around objects while the application is running. This is the problem that Chris described. You don't want to move away objects under your feet while you are working with them. So this is what we do here is we copy all reachable objects out of the live regions that are in the collection set, and we adjust all references that pointed to the old copies to now point to the new copies. This is relatively easy while the program is stopped, as Chris already explained. Problem how to do this while the program is running. Let's see, stop the word compaction. So this is the classic variant of this. Assume you have a couple of references to my object. The object here is this one. It has a header, it has some fields, and DGC copies the object while the word is stopped. So far, so good. Updates all the references, and then you can reclaim this old object, and we're good. Now, if we want to do this concurrently while the Java application is running, you have a situation like this. So you have your object, you have a couple of references pointing into this object. You copy it, and then you update all the references, and then you have the situation. Some references point to the old copy, some point to the new copy. And then you change something in those objects. And one thread probably changes in this field here. The other thread changes in object, the other object here. And which one is which now? Which one is good? At this point, you have an inconsistency in the heap, and this is exactly what must not happen according to the Java memory model. Solution here is we need to coordinate all threads somehow to agree on which object to write to, right? How does that work? So let's see. First of all, each object has a header. This header has very overloaded meaning in the JDK. It contains marking bits. It contains pointer to log objects and the age of objects, and even the hash code is encoded there. So we add one more overloading there. We put our forwarding pointer there. The meaning is if the object is if the header is an ordinary object header, then it's not forwarded. If it's forwarded, then we set a certain bit, which indicates that it's pointing that the rest of the header is a pointer to the new location. So what happens now when we have several threads that want to do some work with the object while the evacuation is running? You have, let's say, one thread on the left side, one thread on the right side here. The way to go is each of those threads makes its own copy of the object. So we actually have 3 or even more copies of the object now. And then each thread tries to update the forwarding pointer of the original object with an atomic compare and swap operation, which means that only one of those threads can succeed. And all the other threads that try to do the same will fail, but will see the pointer of the succeeding thread. At which point it turns out this one wins, and this is the object, the object to write to now. How to do this in code means we need a barrier. Chris already mentioned write barriers. More generally, barriers are snippets of code that the compiler inserts into the, let's say, the code of your application when you access any object in the heap. For example, let's consider this simple example here. You have a get field of an object. This is reading a field out of the object this. And the other situation is we have a put field here. It's writing a reference to the object here. What the compiler would do with this is it would insert a barrier. So this one here, this in gray, is the barrier that Shenandoah would insert after an object is loaded. So this is not a write barrier, it's a load barrier. And it modifies this field. This load barrier ensures the what we just seen earlier, the agreement on which object is which. It actually would insert another barrier here for this, but this is the write barrier for this write access, because we also need to coordinate for marking. But this is not the topic of this talk. I want to show you how this load reference barrier looks like. This is inserted after every load. So this is what it does. It checks if the object that is just loaded, if it's in the collection set, in the working set of our current collection. If it is, then it copies the object. It tries to atomically update the forwarding pointer of the original object. And then if it succeeds, we use this, we won. Otherwise, we use whatever the other succeeding threads just gave us. And that's it. This is a simplified version. The truth is that it's a little bit more complicated for performance reasons, but this is the conceptual correct version. So this is basically how we do the evacuation. This is the very core of the Shenandoah algorithm, if you want to. It solves the problem of the concurrent evacuation and also of update reference. I cannot go into details of this, but this is actually quite easy. Next, so this solves a big part of the problem, the problem of depending on heap size or the size of the live data set in terms of the pauses. We can still have significant pause times that are caused by the roots scanning here. Usually this is taking just a few milliseconds, but if a application uses like many threads, it will go through the roof. I have seen customer applications that are using like thousands of threads, 20,000 threads. Customer sent me a stack dump that was as a zip file that was 70 megabyte in size. So this can go quite out of control. So let's see how we handle this. One thing is the JNI handles here. What does this mean? JNI handles is everything that JNI can give me when you call new global ref, new weak global ref. But it also means for the purposes of the GC stuff like intern strings, synchronizer roots. Synchronizer roots happens every time you do a synchronized statement. Then the compiler, the runtime of the JVM will use synchronizer objects, and this contributes to the root sites. Also stuff like JVMTI and a few other things. Why do we need to handle this while the word is stopped? It's a similar problem like when you scan the root. If you have concurrent modification during marking or concurrent modifications of those objects during evacuation or updating, we need to coordinate for consistency. And the solution is actually the same. We place barriers there whenever stores happen on JNI handles or load reference barriers when loading from JNI handles. The difference to the ordinary barriers is that this is happening in the runtime and in the off-heap references and not on references that are inside the heap. This is the only difference. There is a new problem here. This is the concurrent cleaning of weak JNI handles. In JNI, you can have weak references to weak handles to objects, which mean that if the referent of the object is unreachable, it gets cleared and you cannot access it anymore. When you do this concurrently, you can have the situation that it's not cleared yet, and the GC is clearing all the references, and a Java thread could go there and load the object, even though it should be unreachable, just pick it out and resurrect it, and this must not happen. The solution to this is what we call the weak LRB, the weak load reference barrier, which is inserted in, for example, JNI get object field. It works pretty much like the regular load reference barrier, but it pretends a null value when the referent is actually unreachable. It looks like this. Basically checking if the object is marked here, and if it's not marked, then it simply returns null. This is all. We are going to need this later again for the weak references. I will talk about this now. So we handle the JNI handles. Now, weak references are another class of problem, which is kind of similar to this, but a bit more complicated. Also, in traditional GCs, this can contribute very significantly to the pause times. If you have an application with like thousands or millions of weak references, which this can make your life not very comfortable with this. What does it mean, weak reference processing? Weak references, you probably have used it if you're a Java programmer, are a concept to like hold a reference to an object, but not strongly like usually, but instead so-called weakly, which means that if the referent is otherwise unreachable, then you will not see it again. You will probably see a null value instead. So weak references processing from the point of view of the GC means determine the reachability of the reference of the reference objects, clear the unreachable reference, and then enqueue the unreachable reference objects into their reference queue, so that the application can process them for like cleanup of native resources or something. We have several types of reference objects in the JVM. The ordinary one, which happens when it is not explicit, is implicit when you have a reference field or array elements, is a strong reference. Then we have, with decreasing reachability, soft references, which are usually cleared only when they are unreachable and some like certain threshold is reached in terms of memory pressure. So if memory is full and you have unreachable soft references, they will probably get cleared, which is useful for stuff like caches or something like this. Then we have weak references, which are usually always cleared as soon as the referent becomes unreachable. Phantom reference are a special type of reference which are used for cleanup purposes. The referent here is always inaccessible by the Java program, but the phantom reference will be processed only as soon as the referent becomes properly unreachable. There is one other type of reference which you haven't heard about probably. It's called the final reference. This is an internal type in the JVM for it's used for implementing finalizers. Basically, finalizers are is a method in Java that allows you as a programmer to do certain actions when an object becomes unreachable. Kind of a destructor concept, but not really quite the same. So how does it work? How would this be handled in a traditional GC? I need to hurry up a little bit because I'm running out of time, but let's go over this quickly. So usually how to do this is we mark the reachable subgraph of the heap by traversing these strong references first. This can be done concurrently, like the G1 GC does or the concurrent marking sweep does. And then, but we need to stop as soon as we reach a soft, weak, or phantom reference there. And then, while the word is stopped, we can determine the reachability of those other parts, like look at the weak references and mark through this weakly reachable subgraph and so on. So this needs to happen in this order in several phases because the reachability is decreasing from there. So everything that is reachable by a weak reference is probably also reachable by a phantom reference and so on. I have a little diagram here which visualizes this. So let's suppose we have GC roots here, like local variables. They have strong pointers. The strong ones are the black ones here. We determine that this here is strongly reachable by following these references here, right? It also reaches a weak reference, at which point we will stop marking. And it holds a reference to this object, but this is strongly reachable, which means that this will stay alive. We have a weak reference, we stop here. This holds a reference to an object that is otherwise not reachable, which means this can become cleared. And here we have the example how a final reference works. Those are a little bit special. Final reference means this object here has a finalizer, and we see it's not reachable by anything else here. But itself is referencing, it might be referencing a phantom reference. The phantom reference must not get cleared before it's really becoming unreachable, even by final references. So this is why we have this green graph here. This can only be determined while the word is stopped. Green means it's only reachable by a finalizer. This here is properly unreachable and can be cleared right away by the phantom reference. So let's see. We have a couple. From there, we can make a couple of simplifications to the whole concept of reachability of soft, weak, and phantom references. Soft references are kind of like, they act as like a strong reference. For example, if the memory pressure threshold is not yet reached, it will act as a soft as a strong reference. Or if it's if we actually are under memory pressure, then it acts like a weak reference. So this is basically the same as a weak reference, except for a couple of additional constraints. Weak references get cleared when the referent is not strongly reachable. So this doesn't depend on, it only depends on the property of strong reachability here. Phantom references are basically the same. They get cleared when they are not reachable. The problem is we have final references which must keep phantom references alive, because phantom references must not get cleared as long as they are reachable by a finalizer, even though the finalizer may be unreachable by strong references. Which means overall we need two reachability levels strong for ordinary object graph traversal and finalizable. And with this insight, we can make the marking of this graph here completely concurrent. If we have not one marking bit, but two marking bits, one marking bit for the strongly reachable and one marking bit for finalizable reachable, then we can make this marking process completely concurrent by switching the bit here. So if we come here by marking and it's strongly reachable, we see a final reference, we switch to the other bit and mark the rest here only by the finalizer bit. If we were to have another marking thread later figure out that we have a strong reference, like coming from here to there, this would be upgraded to strongly reachability. Okay, so we solved this marking problem of weak references, but how to clear them? The problem is similar to what we've seen before with JNI weak handles. Suppose you have a reference that is which referent is unreachable, and the application calls reference get on it, and it would normally return the referent that is otherwise not reachable, but would resurrect this object, which must not happen. So the solution is to do the same sort of barrier that we've seen earlier in the JNI weak handles. Pretend that its referent is null, so that we can clear those reference concurrently with the Java program. So I have the diagram again. So this solves the problem of weak references. We have two more classes of problems here, which is one is concurrent class unloading. I don't have the time to go into this detail here. Just saying that it's already implemented in Shenandoah since JDK 14. And we also have the problem of scanning those threads, stacks, and local variables concurrently. This is also very complicated. It would take another talk of this size to explain this. It's currently worked on in my team and is to be included in JDK 17. With all this together, this means that we still have pauses here, but they are basically only for bookkeeping purposes inside the GC, and the pause time here is constant time. Everything else happens concurrently with running Java threads, which should get your pause times under 1 millisecond, well under 1 millisecond even. Yeah, some concluding words on availability of Shenandoah GC. So we don't have any special needs from the operating system, which means it's basically working as it is on Linux, macOS, Solaris, and Windows, as far as we know. Others, if we have other requirements, contact us. We should see what can be done. Hardware-wise, Shenandoah is running on Intel 64 and 32-bit systems. It's running on the new ARM 64 systems. We have work in progress on ARM 32, but it's not done yet. We actually we know that some folks are working on PowerPC ports. It's work in progress. Everything else is not supported yet. JDK version-wise, it's a bit more complicated. The latest release, JDK 15, it's in there. The other ones between JDK 15 and JDK 11, they are not supported anymore. So if you are there, try to upgrade to this. They have Shenandoah, but it's kind of outdated. We have the JDK 11, which is stable LTS. It is in upstream OpenJDK since JDK 11.0.9. We also have a backport of Shenandoah in JDK 8. It is supported and ready for production, but it's not in upstream JDK yet. JDK 16 is just around the corner. We have a couple of new features in there too, but it's not there yet. Yeah, context. So if you information about Shenandoah you will find in this wiki page here that's mentioned, or if you have any questions on this mailing list, or contact us on Twitter. This is my handle. This is Alexei Shipilev handle, which is also contributing to Shenandoah. Yeah, and with this, I'm done. Thanks.
Thank you. Thanks, Roman. Thank you to you both. I'm just looking. I don't see any extra questions in the comments section at the moment. The link to the Slack is in there. So obviously, if anyone wants to continue the conversation about what we've heard this evening, feel free to do so. If you think of anything at a later date that you want to ask, obviously Roman has just presented us with some contact details there as well. But look, I want to firstly thank both speakers, obviously. Oh, I think we might have a question. Yeah, there we go.
Well, kind of. We are not evacuating all regions. We only evacuate regions that we find enough garbage in. So this is it. New memory allocations happen only in empty memory regions, and this is actually a typical concurrent GC problem. We need to start collecting while we still have enough free memory to actually fulfill the allocations and the evacuations by the GC. So this is a common concurrent GC problem. Figuring out when to start the GC. So yeah.
Cool, thank you. Unless any other questions come through, I just wanted to, I was saying thank you to you both for your time and your presentations, and to some of the other people from DiffBlue who I've been speaking with and putting this together. Thank you to all of those people as well, and to Beth, who works for TRG alongside myself, who helps us run our events. So thanks to everyone that's put this together. Thank you to everyone that attended. So yeah, as most of you know, we try and run these as often as we can. We're trying to do monthly meetups, so keep an eye on the meetup page. On my jumper here, it does actually say The Roundabouts. That's our meetup brand. We have 7 different meetups. So if you go to the roundabouts.co.uk, you can see not just about the JVM, but if any of you are interested in JavaScript, DevOps, we do a testing meetup. We've got a more general agile one. That's all in there as well. Before we go, there is another question, Roman. Just I'll read it out. Here we go. Yeah.
When are the empty regions released for all allocations? Yeah, at the end of the update references phases. Exactly. There's a special case when we figure out that after marking that a region has absolutely no reachable objects in it, we can reclaim them immediately, which happens more frequently than you would think. So yeah, we can reclaim a couple of regions right after marking and some more after updating all the references.
Cool. So that's it really. The like I said, the Slack channel is in the comments section, so you can find the link there. Obviously, as I mentioned earlier, if you do put anything online on your social media, or just hashtag JVM Roundabout, like I said, that does help us get the following to be even bigger. So thank you, everyone, and we will hopefully see you in February. The details should be announced very soon. Thank you, and thanks again, Chris and Roman.
Yeah, thank you.
Yeah, thank you.
Bye.
Bye now.